Welcome to the deep dive. Today, we're not really focusing on the output of code, what it prints or calculates. We are going much deeper into the underlying architecture of well-structured code, specifically the silent rules that govern how a language like Python organizes all its information.
That's a perfect way to frame it. Our listeners provided this really great collection of technical notes. They cover namespaces, modules, scopes, all the way to refactoring. And look, for anyone building software that needs to last longer than a weekend, these concepts are just foundational.
Right. It's not just theory.
Not at all. This kind of structure, managing names, controlling visibility, this is what stops a big project from collapsing into just an unmanageable mess. It's all about managing complexity, ensuring readability, and, guaranteeing that the code can actually last.
So the mission for this deep dive is to really understand the rules of the house. How are names organized? Where can they be seen and used? And what's this continuous process needed to keep that structure healthy? I mean, if we boil it down, this whole conversation is about preventing unintended consequences, right?
Exactly. You use structure to stop name confusion, rules to stop accidental changes, and a process to stop, well, decay.
Okay, let's unpack this, starting with the fundamentals, the containers.
Sure. Anytime you have more than, say, a handful of functions, you immediately run into the problem of identity. You need a system to uniquely identify everything, every function, variable, class, without it all becoming chaos.
And that system, that's where the namespace comes in. Our sources define it as basically a collection of identifiers of names that belong to something specific, like a module or a function.
I think collection is good, but I like your idea of a mapping system better. It's more active. Yeah. A namespace is like a map. It links a human-readable name, like calculate tax, to the actual object in memory. Think of a giant library. The namespace isn't the book, it's the little Dewey Decimal label on the spine that tells you exactly where that book belongs.
And its whole purpose is just grouping related things, all the math tools in one place.
Precisely. And if the namespace is that organizational system, that label...
But you need a room to put it all in. Is that where the module comes in? The actual architectural container?
That's it, exactly. The module is the physical container. In Python, this is usually just a single file, a file with definitions and statements you want to use somewhere else.
So when you import something, you're just bringing in that file.
You're bringing in that file and, crucially, its entire distinct namespace. And here's so what. This is the key insight for scalability. Each module has its own independent namespace. Think about Python's huge standard library. It's just a massive collection of modules. And because of this, you and I can both create a function called reset counter in two different files. And as long as we access them through their module.resetCounter versus module.b.resetCounter, they don't clash.
No name collision.
Zero name collision. And that ability to reuse names without confusing the computer is absolutely vital for letting teams work independently.
It's architectural isolation. It stops the spaghetti mess before it starts. But, that very separation sets up our next problem.
It does.
Once you have these names locked away in their modules, you need very strict rules about how they can be accessed from the outside. We're moving from containment to accessibility. So we've got the containers and the names inside. Now, the big question is visibility. Where are these names actually usable? We're talking about scope.
Scope is, it's essentially the security perimeter around a name. It defines the region of code where you can actually access an identifier. If you try to use it outside its scope,
the program just says, I don't know what you're talking about.
Exactly. It enforces discipline. And in Python, there are really three main scopes you need to understand. There's a hierarchy. First, you have the local scope. This is the most restrictive one. It's only for names declared strictly inside a function.
And the parameters you pass into the function count as local too, right?
They do. They're local. Think of it like your immediate desk space. The notes right in front of you are local to you.
Makes sense. Okay, so what's the next level out?
Moving outward, you get the global scope. These are identifiers declared in the current module, so the file itself, but outside of any particular function.
So like a shared filing room for the whole office.
Yeah.
Anyone in the building can go look at those files.
That's a great analogy. And then finally, the widest scope. The air we all breathe.
The built-in scope.
The built-in scope. These are the names that are just always there. Things like print, input, len. The foundational tools the language gives you.
Let's focus for a second on the interplay between local and global, because I think this is where the rules can feel a little counterintuitive. There's a big difference between just looking at a variable and actively changing it.
That distinction is absolutely key. Accessing is pretty easy. A function can look out into its module's global scope and read a global variable. That's fine. It's one way.
But the second you want to reach out from your local desk and change what's in that shared filing cabinet.
Python puts up a pretty serious speed bump. And this is where it gets really interesting, because it shows Python's whole design philosophy. If you want to update a global variable from inside a function, you have to explicitly use the global keyword.
And if you don't, if you just say myvar equals 10 inside a function,
Then Python assumes you're creating a brand new local variable with that same name. Even if a global variable with that name already exists, it creates a local copy.
which sounds confusing at first, but it's actually a brilliant defense mechanism, isn't it?
It is. It prevents one of the most common and dangerous bugs, which is called shadowing. Without that rule, you could accidentally overwrite a critical global setting from a tiny function somewhere and have no idea why your program broke. By forcing you to use the global keyword, Python makes you state your intent. You have to say, I am consciously changing the shared state.
I really appreciate that emphasis on intent. It's a check on power. Okay, so let's flip this around to the computer's perspective. When you call a name, how does the interpreter decide where to look first?
It's relentlessly consistent. It doesn't guess. It has a fixed search order, a precedence rule for lookup. It guarantees that the most specific version of a name is always found first.
And that order is?
It follows what's often called the LGB rule, from most specific to most general. First, it checks the innermost, the local scope, the function you're in right now. If it finds the name there, it stops, the search is over.
It never looks any further.
Never. If it's not found locally, then it moves outward to the global scope, the module level, the shared filing room. And third, only if it's still missing does it finally look in the built-in scope, the language defaults.
So LGB, local, global, built-in. That's the ironclad guarantee. It prioritizes what's closest to the action.
And that predictability is everything. Only if it searches all three, local, global, and built-in, and finds nothing, only then does your program crash with a name error.
Okay. We've built the foundation. We have the containers, namespaces, and modules, and the strict rules for using them, scopes, and the LGB lookup. But any structure, no matter how well designed, starts to degrade over time. So now we have to talk about the process of keeping that structure clean. We have to talk about refactoring.
Yes, refactoring. This is sort of the grown-up part of programming, and it has a very precise definition in our sources. It's the process of restructuring existing code without changing its external behavior.
And that part is key, isn't it? The user on the outside sees no difference at all.
None. But the structure on the inside can be radically improved.
This is a concept that can be hard to sell to managers or clients. Why spend days changing something that already works? If the output is identical, why invest the time?
It's the classic conflict, right? Short-term speed versus long-term viability. The answer is technical debt. When you leave messy, complicated code in place, you are taking out a loan. Refactoring is just paying down that debt. It improves readability, maintainability. It makes the code cheaper to change in the future.
It's preventative maintenance, not really feature development.
Yeah.
So what does that look like day to day? The sources gave some really specific, actionable steps.
It starts with clarity. One of the simplest, most effective things you can do is improving code readability, just renaming things. If you have a variable named X when it should be customer recorded, that's a refactoring task.
Sure. Clarity reduces the cognitive load for the next person. And then there's simplifying the architecture itself.
Yes, simplifying code structure. This usually means tackling those monster functions that do 5 different things. You break them down into smaller pieces. Smaller pieces are easier to test, easier to read, and way easier to debug.
And you have to tackle repetition.
Yeah.
I've heard that if you copy and paste code more than once, you've already made a mistake.
That's the heart of it. Removing redundancies. Duplicate code is a breeding ground for bugs, because if you fix an error in one copy, you have to remember to fix it everywhere else. It's a nightmare. Removing that redundancy gives you a single source of truth.
Okay, that makes a lot of sense.
And while the core rule is don't change the behavior, sometimes better structure leads to other improvements. For example, optimizing performance. You can make the code run faster as long as you verify that the final output is functional identical.
So all of these things, renaming, simplifying, removing duplication, they all funnel into this one overarching goal.
Enhancing maintainability. It's all about future-proofing the work. Making sure the next person to touch this code, whether it's you in 6 months or someone new next week, can do it safely.
And this brings us full circle, right back to modules.
It does. Good refactoring includes organizing the architecture itself. The sources mention using an import guard, for instance. That's a small bit of code that controls what happens when a file is imported versus run directly. It makes your modules predictable.
And the notes gave a really clear example of this, refactoring the test code itself.
Yes, a key step, moving all your tests into a separate dedicated test module. This separation ensures your testing setup stays clean and distinct from the production code it's supposed to be testing. It's just organization at every single layer.
Right. Keep the core structure clean and keep the scaffolding around the core clean too. So let's bring this all back home and wrap up our deep dive. We've covered a huge amount of foundational ground today, all centered on predictability and control.
We did. We saw that you need really 3 non-negotiable things. First, define borders, the namespace to hold related names, and the module as the container to prevent those names from colliding.
Second, you need strict immigration rules. That's scope, local, global, built-into control visibility, and that ironclad LGB lookup rule so Python resolves names consistently.
And third, a maintenance schedule, refactoring, the continuous process of improving the inside without changing the outside. Look, this knowledge isn't optional for modern software. It's how you turn abstract ideas into code that can actually grow and scale with a team.
Absolutely. You have to master the rules of the house before you can start renovating. And speaking of renovation, we ended with refactoring, this process of improving structure without changing the output, which leads me to this final provocative thought for you to consider. And it comes directly from that hint in the sources about separating test code. Since the primary definition of refactoring is restructuring code without changing its external behavior, you need absolute certainty that you haven't broken anything. So what foundational mechanism hinted at by the need to organize test code is the indispensable foundation that gives developers the confidence to actually perform refactoring safely. What protects the code's integrity during that internal renovation, that's your mission for further exploration. A perfect note to end on. Until the next deep dive.